today, I'm afraid. I got some allergy attack, and I just feel like I felt like I had brain damage. So maybe that's good, though, because it's a really hard lecture, and it'll slow me down. Is this thing on? So any of you who are good note takers, could you take particularly good notes today? Because this is a lecture, the only lecture of the course, where I don't have good notes, and I don't have any good handouts. And so I'm going to try to create one for you, but it'd be great if I got help from some crowdsourcing, you know. I'll give you money. I'll give you $100 each. Delete that, yeah. I can turn the camera on now. No, anyway, so here's how we've been. So I don't know, I mean, the message is so sweet. You know, we have an input, an observation, and there's a hidden state. And there's what they call a belief state, which is the conditional distribution of x given the observations of the input. And if you look at the pair, that turns out to be a sufficient statistic, which is made precise in the notes. I won't get into that. It's called the information state in this field. And it is awesome that it's a controlled Markov chain. And if you look at the notes, I wrote down the transition probability for you. So we know that the optimal, well, we only developed theory in the finite state space case. This is now evolving in an infinite state space. But you know, we can suspect that the optimal input is a function of the information state, because now it's with this as the state, it's a fully observed controlled Markov chain. Voila. But you know, good luck trying to figure out what this is. Now, one of you, please, I hope, you know, perform value iteration for the homework problem, you know, because you just come up with a grid. It won't be that bad, you know. You just quantize, you know, the belief state, and you can come up with it, and you'll actually be able to see the decision regions for when you drive and when you don't drive. There'll be decision region, you know, and you can guess what it is. If you think that you're at the bottom of the hill with high probability, you're going to drive. You know, I mean, it's just it's clear that's what you're going to do. But it'll be fun to see it, you know, see how sensitive it is to the parameters and all of that. I don't know. You know, I mean, the last time that's not quite true. I mean, the last time I taught this course at Illinois, computers were too slow to make this a reasonable assignment. Okay, so a miracle happens when you go to LQG is a non-made clear on Tuesday. So miracle, first of all, is that the belief state is characterized by the conditional mean and the conditional covariance. And I ask all of you, I wish there was more of you than I see here, what is special about Gaussian? There are two things that make Gaussian special. And Anand said it, but he you know, we want to scream this over and over again.
You only need the first two moments.
Yeah, that's the first thing. First is that, yeah. So Gauss is special. One is because of that. Yeah, since, you know, it looks really awful that, you know, the belief state's a conditional density, but it just turns out all you need to know is the mean and the covariance, and you're done. But the second thing that's maybe even more important is that when you look at the cost, the expected cost, actually, why is G special? Not just G and Q. So So Gaussian special because of the fact that the belief state is just determined by the conditional mean and conditional covariance. But here we need both the quadratic and the Gaussian assumptions, because we take the cost and we can always write xt as x hat plus a deviation. We'll get a decomposition like that. You know, that's always going to be true. All right. So here I haven't used anything. I've used the fact that the cost is quadratic, but going from here to here is nothing. Okay. That's always going to be true if x hat's a conditional mean. But under the Gaussian assumption, sigma t doesn't depend on the input. And so this doesn't depend on the input. You know, and that's wild. I mean, you'd think that you could put spiky inputs in and you'd somehow get more excitation in the system. Xt goes crazy, you get a high signal-to-noise ratio, and you'd be able to estimate better. You know? Wouldn't you think that? I mean, you put in a big input, you lower this, you increase the signal-to-noise ratio. That's what anybody would do, right? If you're trying to estimate a signal, you'd like the signal to be huge to swamp out the noise. Why on earth does that not depend on the input? Well, it's magic. So it's just the math. I don't know. I mean, I feel. I mean, I should give you some insight, but I don't think I have any. Just the equations give it to you. It's independent of the input. You can't change that error, but you can't do anything about it. So the fact is, you end up with a fully observed LQG model, and the cost is a quadratic function of the observed x hat. It's an absolutely amazing thing. So that's how you get away with the fact that u star t equals k star x hat t. So the k star is a solution to our Kadia equation, and it's independent statistics. It's completely, statistics are irrelevant completely. But to get x hat t, you need the nonlinear filter. You need to know all the statistics, to make all this work. So here, there's a big discrepancy there. Okay. Now that is a very, very, very fragile example. I mean, that is this fact that you can just plug in x hat t, pretend it's reality, and use the same gain you would have used for the fully observed case. I don't know if there's any other example like that. You know, the same thing. Yeah.
Last class we did an example. One of the things that was asked was, when we arrived at that final result, was because we assumed the mean was 0, but if the mean wasn't 0, there was going to be like an extra constant. Oh,
well, I mean, you mean the mean of the noise?
Yeah.
Well, yeah, it's just like an input then. You know, I mean, just like ut is an input. Yeah, I mean, yes. I mean, if the noise had non-zero mean, and you don't know it, then you get into something freaky. If you know it, you subtract it off. You just consider part of your input. You know. Yeah.
Let me just. I want to look back to see because.
Yeah. Yeah.
What this is saying is that you can control the whole system through only the measure of state data, what you can observe.
Well,
X hat, right?
X hat's a conditional mean, and you see that the cost is going to go up because you have this estimation error term.
What I'm saying is your optimal policy is only a function of your.
That's the crazy thing. I mean, well, the thing is that, I mean, when you solve the Lyapunov equation, like in the fully observed case, you'll see that the gain doesn't depend on the noise at all. It's absolutely irrelevant. All you need is you don't need Gaussian. All you need is zero mean and finite covariance. And you get the same k star. And then in the partially observed case, you just plug in the same k star, but you have to put the estimates there. Yeah. Yeah, it's pretty cool. And there was this real false enthusiasm in the day. Back in the in the 60s and 70s, I mean, Kalman was here, I guess. I mean, this was oversold. I mean, people suddenly were saying that classical control is meaningless. There's a new day. And people were making fun of people who did PID control. It was amazing. And it wasn't until MIT killed a pilot with their MIT rule that people wised up again. It's true, actually. There was something called the MIT rule for this adaptive controller gain. And people got obsessed with mathematical control after Kalman, because it looked like you could just play around with equations and solve a control problem and walk away. It's very much like economics today. It was pre-MATLAB, so you had a lot of mathematical control people who would come up with really cool algorithms and say, wow, this is it, it solves the problem. They'd send it off and walk away. And it's like economics. Economics, there's no ground truth. They don't have a MATLAB. So they come up with a beautiful formulation. They can't go and do an experiment. If they do, they'll devote years of their life. It's just not worth it to them in their careers. And so, yeah, I don't know if it's really causal, but my feeling is that huge disaster made control theorists more introspective. And they actually went back to their roots. They went back to robustness, classical control, and tried to leverage some of those ideas and make them, extend them to multidimensional settings. So when we kill somebody, control theorists go back to our assumptions, unlike some of the fields. That's a fair criticism, I think. I mean, yeah. So anyway, so the thing is that this looks amazing, but sometimes I can give you you know the example. It's like the ball and beam example. You've got a two-linked inverted pendulum, and you only have measurements of the lower angle, and you can go through. You can do all this stuff. You say, "Man, I solved the problem," and of course you can't. I mean, it's so sensitive. A tiny modeling error, the thing just blows up. So in terms of sensitivity, this can be horrible. And it just depends on the context. Some problems are very sensitive, some problems aren't. So you got to be really careful with this stuff. Yeah.
I kind of missed a little bit of the discussion on the importance of number 2.
Well, they're just right there. You see, the fact is that there was a conversion from, well, like here, there's a conversion from a partially observed problem to a fully observed problem, where the observation was the information state, but trying to come up with this feedback law would be impossible. It's so complex. In this case, it turns out that because of this mapping, you end up with exact same problem. I mean, model you started with. X hat t evolves exactly like xt did. It's an LQG problem. And not only that, you can map the cost for the original problem to a cost with x hat as a state. Now, if this depended on the input, we'd be screwed. If this was some complex function of ut, it wouldn't be a quadratic cost maybe anymore. Maybe this would be some incredibly complex function of ut. What if it was algebraic, like ut squared over 1 plus ut squared? You'd say, what the hell, I don't know what to do. But the fact that it doesn't depend on ut, it means it is an LQG problem. It's just awesome. It's incredible luck. Yeah.
We don't know what that second expectation is.
Doesn't matter. We're talking about solving the optimal control problem, And we do, because this is a function of sigma t, which we do know. So we do. But it doesn't matter in terms of, because minimizing this is the same as minimizing that. That's the point. Because that doesn't depend on the input.
Okay.
It's just a constant.
Yeah, well, it's not constant.
I mean, it depends. Yeah, it's a constant. It doesn't depend on ut.
Okay.
Yeah, and it also converges to a constant as t goes to infinity. So we do know this. Once we optimize, we know this because it's a solution to the LQG problem. We know this because it's a function of sigma t. So
yeah. If you're optimizing, your optimization only minimizes the cost. It doesn't. How does your optimization come into play with bringing in, making sure like your x hat t, it's very close to the real thing?
Oh no, it does. I mean, x hat t is optimal. It's a conditional mean. I mean, x hat t is obtained from the Kalman filter.
So what I was thinking is like, if your estimate is real close to reality, then the x tildes will go to 0.
Yeah, but it depends on how much measurement noise there is, how much state noise there is, and I mean, this is given by the trace of that and that. I mean, I'll write it down. you can just show, you can show that, is that the right direction? No, Q sigma 2. Well, it doesn't matter, that's right, it commutes. Trace of AB equals trace of BA. So, you know, so that's just some deterministic sequence. It's crazy. You know, it just evolves independently of everything. And it converges to a constant as t goes to infinity. So, yeah. Yeah, it's wild, you know. And so, but the thing is, it can give you such a false impression. So today's lecture is about the classic example where this kind of plug-in policy absolutely fails. And it's sort of a model for a lot of learning problems. And it's these multi-armed bandits. Okay, yeah.
I feel like
Yeah.
this is something we do a lot in controls, though, because,
Yeah.
like, you know, if we're like designing a control for an aircraft, we linearize the dynamics.
Oh, yeah.
And then obviously we're just measuring like gyroscopes and accelerometers,
Yeah.
estimation. And then
Yeah.
if you're doing like an
LQR.
yeah,
Yeah.
LQR, you're just assuming you have your states after your estimator, then you
Yep.
design that.
Yeah. I think the thing is that you're absolutely right. So typically, what you do in like a lot of like aerospace, I mean, all sorts of standard control problems, is you pretend the system's linear, then you apply this theory. And sometimes it fails miserably. Sometimes it works beautifully. It depends on how good the linearization is.
They also do the sensitivity analysis and all that.
And you have to, and it depends on the sensitivity of the linearization. And maybe, so if your linearization is very insensitive to modeling error, then you can have more confidence that the inaccuracies from the linearization aren't going to kill you. But,
it's
yeah.
like a crazy optimization problem, and then to try to find like the optimal things, I mean, all kinds of stuff.
Oh yeah, I mean, people just don't do that because it's so, it's so complex. If you try to really optimize a nonlinear system, typically, in most cases, you can't. I mean, that's why we need,
I'm saying even the linear system, like subject, like if you're trying to, with LQR, because I work with that, like trying to get your LQR to meet like performance and robustness criteria becomes hyperdimensional.
It depends, and people do use LQG too, LQR. I mean, it's true that. I mean, I went to McGill University where George Ames was the star at the time and developed all the classical control extensions to multivariate systems. And I'm definitely a fan, and that's H infinity, where you explicitly take into account robustness in a state space setting. It looks very similar to LQG when you're all done. It's really very similar, but at least it's more attention to robustness in H infinity control versus LQG.
LQG seems like white noise, right?
What's that? LQG. Well, you're assuming. Well, LQG. Yeah, it's Gaussian, IID, zero mean. Yep, white noise. Yeah.
Because I remember covering that in a robust and adaptive class that I took, and what they did is when they cover observers, they introduce a LQG as like a common filter addition to.
Well, that's what this is.
Yeah.
So X hat. This is from the common filter. That's right. Okay. Okay. So let's shall we? Oh yeah. Go on.
So the next so the QG is special because you can apply the same feedback block to the fully observed and the partially observed process.
Well, these two ingredients allowed us to justify that. Yeah, exactly. Yeah, those two ingredients allowed us to do that. And that requires a Gaussianity, and that requires both Gaussianity and quadratic cost. And like if you didn't, like again, this would be true for any quadratic cost, even if the noise wasn't Gaussian. I don't think this would be independent of the control. Like if you had uniform white noise instead. I have no idea. I don't think anyone knows. Okay, but in the Gaussian, it's trivial for the Gaussian case because you just look at the recursion for sigma t. All right, so let's,
One last question.
Okay.
I recall from previous class that when we're dealing with this, we used to use this thing called the separation principle to gain tune without the noise and then with the noise.
But that's the separation principle. This is called the separation principle. Yeah. So we proved the separation principle. That's really what we did. Yeah. That's one name for this plug-in plug-in principle. And it's awful they call it the separation principle because it suggests it's something universal. But it's so fragile, it's incredible. It depends on these things absolutely critically. Yeah. All right. So we've got that. Well, no, I'm going to kill this now. So I've spent the last few weeks combing the websites for like the state of the art on bandits and tutorials on bandits, because like it's became hot again maybe 10 years ago, and I found so much stuff, and some of it some really cool expository stuff, but then really flaky on the math, and some really cool math stuff, but so technical it's absurd. And then, last night I had allergy attacks. I couldn't think. I thought I'll do it in the morning. And this morning I was sneezing all over the place. So I've got these scribbled notes all over the place. And so it's not but sometimes those are my best lectures. We'll see. But you can imagine what a bandit is. It's multi-on bandits. Bandits are slot machines, basically. And you pull an arm, you get a reward. Usually it's negative. You pull arm again, it's a negative reward, and you keep pulling. So a multi-arm bandit is when you get to go and you pull one arm, and you say, that's a bad machine. And you went over and you pull this arm. That's a bad machine too. And you went over and you keep on. You've got maybe a choice of arms, and you keep pulling. And one of them is going to make you a lot of money. One of them is going to kick ass, and maybe the rest are no good. And so what are you going to do? Yeah, well, hold on before you, Neil.
Well, do they call it a bandit because your expected return is negative?
No, because it's a bandit because it comes from Las Vegas, way of thinking. They're stealing money from you. Yeah.
The thing that I always ponder about that problem, maybe I'm completely wrong. It's like if you're pulling like different arms, the probability of winning, it's independent from one machine to the next, so the probability doesn't change, right? Well,
no, we'll solve this. No, we need assumptions. So we need to know what we mean about this. I mean, if we're talking about all the slot machines being identical, they're all the same manufacturer, they all have the same probability of winning, there's no reason to go from slot machine to slot machine. But the thing is that this has way broader. Well, first of all, we're going to look at bandits. I'm going to define what I mean by that. And one of the key things I'm trying to get across is this idea of exploration versus exploitation. And by exploration, it's what I was saying before, it's like high SNR. High signal to noise ratio. I'm talking to you're all supposed to be like signals and systems types. SNR means signal to noise ratio. Okay, so I'd like to be able to boost up the signal so I can learn. And that's what we saw wasn't important in the LQG problem. I could make the input huge, hoping to make the state huge and get a higher signal to noise ratio. I could learn the state better, but we found you didn't. So it doesn't help at all. So exploration in the LQG problem doesn't come up. Yep.
As an example, would that be just putting a lot of money in one turn?
Yeah. Well, I guess so. Yeah. For slot machines, it'd be like, well, no. Because then you only learn anything about one machine. Yeah. All right, we're going to get to that. Okay. So, yeah. So I mean, I would. His example. I wish I had, use a computer in today's lectures, but. So there's, the biggest thing is medical trials. I'll give a really important example first and then some joke ones. But medical trials, I've got 5 different medicines that might cure cancer, you know, and I've got a bunch of people who are volunteering. Everyone with cancer is volunteering to use this. And, you know, maybe only one of these 5 treatments works. So what I'm going to do, I'm going to kill 80% of these people. You know, I'll spread it out evenly. I'll divide into 5 groups. You know, maybe that's not very ethical.
In theory, that's what they would do.
Yeah, yeah.
On double blind and all that, although phase 1 clinical trials, they don't.
Yeah, but still, it's like there's some ethical issues there. So it'd really be, if you're doing this over a long period of time, and also you're learning, maybe things are, you know, maybe it's already been approved, but you're trying to learn over the years which one's best. So it might be that they all have some benefit, but one of them has the most benefit. And so you'd like to be able to go and, you know, you'd like to be able to go and give more. Well, ideally, you'd like to give the best drug to everybody, you know. So the the exploitation. You want to give the best treatment, but you don't know what the best is, you know. And so the exploration is some, yeah. 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 And so the exploration is learn what is best, and you see that conflict. You know, they're totally at odds with each other. You know, you've got to kill a few people. But you know, I mean, there's, you know, in industry, well, that's another serious one. It's oil exploration. You know, it's really clear, you know, what exploitation is there. You know, I mean, I mean, you know, you're going to, you know, there's some places here with a lot of oil. You're going to drill. You know, but maybe, you know, maybe over in St. Petersburg they've got more oil. And it might be very costly in that case to explore. You have to bribe a lot of state officials or something. Yes, there could be a real cost to exploration.
That you will use to decide to switch from one phase to the other, decide that will be like a cost function. So
the question is metrics for deciding how to do this. That's what we're gonna knock off in the next hour. Okay. Yeah, also in advertising. And you know, again, I'm not going to. I don't have to write down. Just think about it yourselves. I mean, you know, this is huge. I mean, hugely valuable to advertising companies. You know, and it's also cool. I mean, you think about it. You know, a lot of these things are very dynamic as well. I mean, you know, you've got something that maybe it was the best approach for advertising, and then you annoy people after a while. So there could be dynamics, you know, that I need to explore just because things, you know, what worked in the past doesn't work today. So there's dynamics in this one for sure. And I'm going to ignore dynamics here. I'm going to be more in things like medical trials, where there's a handful of treatments, one of them is best, and we'd like to find out which one that is, and at the same time we'd like to save as many people as we can. Okay. So I want to first give like a Bayesian example. Well, actually, first some notation. well, yeah, a little bit of notation. We have an action space with k arms, and we have a reward. So if ut is action A in this set 1 through k, I'm going to get a reward which is distributed according to this density, you know? All right? And yeah, and the goal is to maximize the total expected reward. Now, I could make this go to infinity, and I could put a discount factor. Why do I, in this case, I don't look at the average cost? You know, there's a setting where I take back everything I said about the average cost. Because remember, look at the first example. You know, in the long run, in this case, we really are all dead. You know, so I really believe in average cost criterion for a lot of the dynamic problems we talked about, the speed scaling model, all sorts of problems like that, where stability is a big issue. But here, you know, there's this really important short-term value, you know, that's really critical. So looking at this finite time horizon or discounted horizon, a discounted infinite horizon, I'll put a 0 there to be consistent with before. One of these guys is way more justifiable than the others. Okay, and what's done in practice actually is, now let's look at an example before I go any further with notation. So an example is a Bayesian setting. And it's a little bit different than this in a way. It's a little more structured than this. So let's take the rewards to be Gaussian.
Is UT discrete here?
What's that?
Is UT?
Oh, always is, right?
Values?
Oh, no, it's right there.
Oh, okay.
Yeah, my action space is my input space always. And here's where, yeah. Let's do it like that. So I'll put an RA bar there. How's that? I've got the reward is Gaussian, and the mean is some R bar A, and the variance is this. And I know these things. These are known. And in this case, no, hold on. Hold on a second. That's not right. Sorry. I'm getting myself confused. 1 second, everybody. That's not, excuse me. screw it. I'll come back to that. Everyone just ignore what I just wrote down, because it's a little bit different than the standard setup. All right, so yeah, I can see why I'm getting myself confused. So I'm going to come up with a Gaussian, like LQG model to try to model this. And I'm going to take a state process, which is constant. You'll see why I'm doing this in a moment, okay? And I'm going to take my reward, to look like that. And again, I'll explain all this, and I'll write it down and then explain it. We're getting there. So,